Hello everyone. Today we'll be covering the second lesson of AS Chemistry CIE A-Levels, code 9701. This will be a two-part video, and in the first part we'll be covering a recap of the three types of bondings that are taught in IGCSE, introduction to the terms lone pairs and bond pairs, and introduction to a new fourth type of bond. And we'll also be covering the carbon hybridization and how to use the hybridization of an atom in a bond. And lastly, the definitions of sigma and pi bonds. And the rest of the lesson we'll be covering in the second part. So in IGCSE, you recall that you've been taught three types of bondings. One is ionic, the second is covalent, and the third is metallic. An ionic bonding, it's formed by electrostatic forces of attraction between oppositely charged ions. So for a very basic example is Na plus and Cl minus. Because they have a positive and negative charge, they are oppositely charged and therefore are electrostatically attracted to each other. And ionic compounds always form a giant ionic lattice. This is the structure they have. This is their structure, and the giant ionic lattice is basically like repeated numbers of Na and C, like the Na plus and Cl minus ions, infinite times, to form a large solid. Okay, relatively large solid. That's the ionic bond. In covalent bond, it's formed by sharing of electrons between two atoms. So an example would be oxygen, O2, right? It's formed by sharing of electrons between, it's a double bond. It's sharing of electrons between two oxygen atoms. And there's also lone pairs, but we'll get into that later. And another example would be OH, hydroxide ion. So it's sharing of electrons between hydrogen and oxygen. And there's an overall charge minus. And the third type of bonding is between metallic. The third type of bonding is metallic, and it's formed for metals only. And what this is also a giant structure, but instead there's like let's give an example of a metal. Calcium. Okay, so calcium. Now calcium has valence electrons, and the usual the valence electrons are two, right? Two valence electrons, and so the two electrons are delocalized in this lattice. Okay, and there's Ca. These are all Ca. Okay, 2 plus Ca 2 plus, and the valence electrons are delocalized, so it's all over the metallic lattice. Okay, and there's an attraction, like an electrostatic force of attraction between the delocalized electrons and the cations, and that is what forms the metallic bond and holds it in the lattice shape. Now, regarding the structure of covalent bonds, there's usually two. The first structure is giant molecular. Common examples are diamond from IGCSE, diamond, and silica, SiO2. Even Si has a giant molecular structure. And another example, no, not another example, the second type of structure in covalent bonding is simple molecular. Okay, simple molecular. In giant molecular, it has a higher boiling and melting point, and in simple molecular, it has a relatively lower boiling and melting point. So therefore, these are usually liquids or gases in room temperature and pressure, whereas these are solids. The reason is because of the bonds that are broken to convert them from solid to liquid and liquid to gas. But we'll get into that later when we cover the intermolecular forces. Anyway, so those are the three types of bonds that were taught to you in IGCSE, and that was just a small recap of that. And now, let's get into the terms lone pair and bond pair, and these are very important, and you'll see this many times in your AS and in your A2 level, so it's something that it's of utmost importance. Lone plus bond pairs. So lone pairs are basically okay. Before all that, what I'd like to share with all of you is that usually electrons, they occur in pairs, as you see in orbitals also, like in the 1s, they occur in pairs, right? So that is something you have to get used to, that electrons always occur in pairs, or they prefer to occur in pairs. And so what happens is, let's say there's an oxygen bond, okay, oxygen double bond. Okay, there's a double bond between two oxygen atoms, and each oxygen atom has how many? 6 valence electrons, right? So it shares 1 2 1 2. Each of them share 2 2 here, and they have 4 to themselves, okay? And this has 2 here, and this has 2 here, right? Now another way to represent this would be like this, okay? And so what the lone pairs are basically is the pair of electrons that are not involved in the covalent bond. Okay, so for this oxygen atom, these would be the lone pairs, these would be the lone pairs, and for this one, these would be the lone pairs, this would be the lone pairs. Okay, and these electrons, like a pair of these bonding, the electrons that are responsible for the bonding between the two atoms, are called the bond pairs. Okay, these are the bond pairs, whereas these are the lone pairs. Another example would again be the hydroxide, right? This is the bond pair. You'll see as to why this is important later on, but just accept this as a theory for now. And in bond pairs, for bond pairs, there's also a concept of electronegativity, which means that one atom involved in the covalent bonding is more likely to pull the electrons towards itself. But that we'll be covering the next part. Okay. Now I'd like to introduce a fourth type of bonding, and it mainly comes in the transition elements, but it's also asked in the AS level. And the fourth type of bonding, which is new for IGCSE students, is dative covalent, or you could also say that as coordinate bonds. And what it basically is that a lone pair, like normally, for example, there's NH3, right? H, and to a lone pair, like a lone pair for the nitrogen. This is the NH3 molecule, right? Now, what a dative covalent bond is that the electrons are not shared, but is completely donated by an atom to another ion, most probably. So, and the two examples for dative covalent bonds in your syllabus are NH4 plus and Al2Cl6. Okay. Now, I'll show how exactly it forms a dative covalent bond. So for NH, okay, let's just ignore Al2Cl6 for now. For NH, what happens is there's a hydrogen, okay. No, there's 3 hydrogens that form bonds with the central nitrogen atom, and it has a lone pair of electrons, okay. And there's an H plus that just happens to occur for whatever reason, okay. And this electron, like a dative covalent bond is formed when these lone pair of electrons are donated to this this hydrogen ion, the H plus, which forms an H, and because these two electrons are donated to the hydrogen, what happens is it's still the nitrogen's electrons, but it's this. And normally we represent NH3 like this, right? The single bonds and the lone pairs, where you represent the dative covalent bond. This is a covalent bond, right? This is covalent. You represent the dative covalent or the coordinate bond with an arrow towards the ion or atom that's receiving the electrons on the receiving end. So this would be a dative covalent bond, dative covalent form of NH4+. Yeah, I hope that makes sense. And the reason why this has a net positive charge is because it has more positrons, like not positrons, a higher proton number than an electron number. Okay, that's the first example of dative covalent bond. And the second example of dative covalent bond is the Al2Cl6. So unlike most metals and non-metals, when they form a bond, they form ionic. In Al2Cl6's case, it's covalent bonds that are formed. So normally they occur in AlCl3, right? And this is the AlCl3 structure. But a more stable structure is possible in certain conditions. And what happens is there's another Al, right? This has Cl, this has Cl, and this has Cl. What happens is a lone pair from this chlorine atom is donated to this Al, and a lone pair from this chlorine atom is donated to this Al. And this is the dative covalent bonding that occurs in Al2Cl6. A better way to show it, like I'll just like a mechanism form, so it's more understood. So there's Al, right? Electron shared with Cl, electron shared with Cl, electron shared with Cl. Okay. And this Al, it's going to be a bit more complicated to draw. Okay, that's what happens. Al shares electrons with Cl, shares electrons with shares electrons with Cl, and shares electrons with Cl. And this one also donates its electrons to the Al. I won't draw the lone pairs here because that would just take long, but accept this as one. So this, okay. That's the lone pairs, yeah. Lone pairs, bond pairs. This is the lone pair that's donated to the Al, and therefore it forms a dative covalent bond. Now that is the new type of bond that's introduced in the A-level syllabus. Now, that's all well and good, but there's also something else that you need to keep in mind, and that is hybridization. Now, another thing to keep in mind is that no bonds are purely covalent or purely ionic. No bonds purely covalent. Okay, not no. Most bonds not purely covalent or ionic. What I mean is that whenever, like, for example, a covalent bond is formed, like let's say between an oxygen and a hydrogen, the bond won't ever be purely covalent, as in like the electrons won't be shared equally. The bond pairs will either be attracted to one or the other. Okay, and the only time that it's purely covalent is when it's formed between two atoms of the two same atoms. Like for this one, H2, right? The atoms are the same, and therefore the covalent bond is, well, almost pure, almost like it's almost purely covalent, because the bond pair is shared almost equally. The same case with wait, just give me a minute. The same is the case with ionic bonds. Whenever an ionic bond is formed, for example, between Mg and NO3 and 2, right? This Mg2 plus, what happens is, the Mg2 plus, it distorts the shape of the NO3 minus anion. And that is a distortion that's taught later in the AS, sorry, not AS, in the A2 syllabus. But my point is that most bonds are not purely covalent or ionic. Okay, now let's get into hybridization. It's nothing too complicated. No, it's hybridization. Apologies for the spelling error. Hybridization. And the hybridization usually asked for is carbon in the organic chemistry questions. Now, we don't have to go much into details for hybridization in our syllabus, but you know, in covalent bonds, normally we just say that the electrons are shared and therefore the bond is formed, right? Well, what actually happens is when the electrons are shared, there's an orbital overlap between the two atoms that the covalent bond is formed between. And what hybridization states is what hybridization is basically a description of that bond. So for instance, how do I say this? CH4, methane. It's a very common example. And in CH4, what happens is, I'll just draw a normal form, not the 3D representation. Yeah. What happens is there's an orbital overlap between the p orbital of the carbon, because that is the valence orbital, and the s orbital of the hydrogen atom, right? And each hybridization, sorry, not each hybridization, the overlap between the orbitals is something like this. Okay, and you see here that this is the s orbital and this is the p orbital, right? Because it's more lobed and this one is more circular. And this one is it's almost like 75% p orbital and 25% s orbital, like the characteristics. And therefore the hybridization of this carbon atom is sp3, right? Because 3 by 4 is 75% and 1 by 4 is 25%. Now that's like, there's more in depth of hybridization, and if you would like to find that out, I'd suggest watching another video that describes hybridization in depth. But what we need to know for our syllabus is the hybridization, how to deduce the hybridization of an atom, and what its impacts are on like the molecule itself. So the hybridization impacts the characteristics of the molecule, which has not gone much into depth, and it also impacts the shapes of the molecules plus the bond angles. We won't be covering shapes and bond angles in this part of the video. We'll be covering it in the second part, but just know that these are what these two are influenced by the hybridization of an atom. Now firstly I'd like to say, firstly I'd like to show you how to find out the hybridization of an atom. Another common example is ethene. Okay, H, and there's an H there, there's an H there. So how would you find out the hybridization of this? How would you find out the hybridization of this carbon atom or this carbon atom? It's the same because they have equal. It's the same because they're identical, right? So how would you find out the hybridization? The easiest way to find out the hybridization is by sterics. Oh, okay, wait, my mistake. I'm making a lot of spelling errors today. Sterics number. Okay. Now, what exactly is the sterics number? I'll just be erasing this ethene molecule for a bit. Okay. So, what exactly is the sterics number? The sterics number is calculated by, it's the sum of the number of lone pairs on atom plus the number of sigma bonds formed by the atom. Now what is a sigma bond? I'll be covering in a bit, but it's basically when single bonds are formed, right? So when there's a CH, this is a sigma bond. When there's a C double bond H, this is a sigma and a pi bond, because when there's one bond present, there's sigma, and when there's two bonds present, there's sigma and one pi, and when there's three bonds present, there's one sigma and the other are pi, 2 pi. So 1 sigma, 2 pi. This is nothing mathematical, it's purely the type of bonding. So the number of sigma bonds formed plus the number of lone pairs on an atom. Okay, remember that formula or note it down. You can rewind the video and note it down. Anyway, so let's redraw the ethene molecule. There's an H here, there's an H here, there's an H here, and there's an H here, right? So what is the hybridization of these two carbon atoms? Now let's see it individually. So what is this? How many lone pairs are on this carbon atom? Well, a carbon has 4 valence electrons, right? So it shares 1 electron here, 1 electron here, and it shares 2 electrons in the double bond. So all of its lone pairs are gone. So the sterics number is 0 plus. Okay, wait, before deducing the hybridization for this, sorry, I'll give you the table of values. So the sterics number, I forgot I gave the values. I didn't give the values, and the hybridization. Okay. So if the sterics number is 2, the hybridization is sp. It's 1, but we just ignore it because, well, when it's to the power 1, we just don't write it. When the sterics number is 3, the hybridization is sp 2. When the sterics number is 4, the hybridization is sp3. And these are the hybridizations that usually come in your syllabus. Okay. Now note that table down, and let's get back to our friend, the ethene molecule, for the third time. Okay. So what is the hybridization of these two carbon atoms? Well, the number of the number of lone pairs on the carbon, as before mentioned, is 0 because it shares in like the valence electrons in the bonds formed. How many sigma bonds are formed? So there's one sigma bond, there's a second sigma bond, and there's a third sigma bond. And since since it's a double bond, it's also a pi bond, right? So 3 sigma bonds plus how many lone pairs? 0, and therefore the sterics number is 3. And when the sterics number is 3, you refer back to your table. The hybridization of each of the carbon atoms is sp2, and that's how you find the hybridization. And whenever the hybridization is sp2, it has a 120-degree bond angle, and the shape formed is trigonal planar. We'll get into the shapes and all that in the next part, but yeah. But whenever the hybridization is sp2, the molecule is planar. That's something that you should always keep in mind. And it's often asked, even if like you don't have to state the bond angles or the shape of the molecule. You have to know that whenever there's an sp2 an sp2 atom involved, the molecule is planar. So let's make it a bit more complicated, and the best examples for these are organic chemistry, organic molecules. So I'll just continue with organic molecules. Okay, now I'll just draw the displayed formula because that'll be easier to work on. For those of you who recall organic, you will recall that this is 3 carbon atoms, so prop 1 in, right? Well, actually, there's only one possible. So like it's propene. Okay, this is propene. Now, if I ask you to find what is the hybridization of this carbon atom, and this carbon atom, how would you find out? Okay, that's your first question. Hybridization of each C atom. And the second question is which parts of is the entire molecule planar? Is the entire molecule planar? Feel free to pause the video and have a go yourself. Well, regarding each of the carbon atoms, let's refer back. Okay, wait. I made a mistake on. Okay. Now feel free to pause the video again and have a go yourself. Okay, so for each of the carbon atoms, you see the sterics number for this would be, so how many lone pairs of carbon are available? None, because all are used up in the bond. So 0 plus how many sigma bonds? 1, 2, 3. So 3 sigma bonds. And therefore the sterics number is 3. So the hybridization of this carbon atom is sp2. Similar for this, because 1, 2, 3, right? 3 sigma bonds, 0 lone pairs available. The hybridization of this carbon atom is sp2. What about for this carbon atom? You see that the number of lone pairs available again are 1 to 0, so 0 lone pairs, plus the number of sigma bonds are 1, 2, 3, and this is also sigma bond because it's a single bond, so 4. Therefore the sterics number for this is 4, and when the sterics number is 4, the hybridization is sp3. Okay, now what about the second question? Is the entire molecule planar? If you guess no, then you're right. The reason is because an sp3 carbon atom is involved. Only like if I just said it, whether over here it's planar, you'd be right, because this is an sp2, so it's planar. But whenever there's an sp3 carbon atom involved, the shape is tetrahedral, and the bond angles are 109.5 degrees. Okay, and what happens is, so I'll draw a 3D representation. That's an H, that's an H, and yeah, that's what's happening. See, CH2, right? That's, yeah. So this one is above, this one is on this side, this one's going behind, and this bond is coming front. So it's not a planar molecule because the bonds are heading out in all directions. Yeah, that's pretty much it. And now let's finally get into what sigma and pi bonds are. Now, you don't really need to go that much in depth to this as well. The definitions are sufficient, but I'll anyway just say what they are. Sigma plus pi bonds. Yeah. The sigma bonds are formed by overlapping between the orbitals and sigma bonds. They're formed by overlapping, like head-on overlapping of the orbitals, yeah, and the electrons are less delocalized, therefore forms stronger bonds. Okay, that's the definition of sigma bond, and the definition of pi bond is lateral overlapping of orbitals. Okay, electrons are more delocalized, therefore forms relatively weaker bonds. Okay, so these two are the definitions. It's best if you note it down, or because you might be asked. But them asking definitions for sigma and pi bonds are rare. If you just understand what it is, like the lateral overlapping and head-on overlapping, that's good enough. Now I'll just dot this in a diagrammatic representation. So a very simple example is again CH ethene, a very basic example. H, and there's an H here, there's an H here, right? So the sigma bond is formed between these two carbon atoms, right? So there's a sigma bond here, like it's between these two. There's okay, ignore the shape, but yeah, basically those are the sigma bonds. The sigma bonds, they rarely ask the shape for. But what happens is the pi bond formation. This is what's interesting. So I'll just draw okay, no, wait. The pi bond formation is what's interesting. So the p orbital shapes are like this, right? And the reason why I'm saying that it's a lateral overlapping is because this orbital, this part of the orbital is attracted to this part of the orbital, and this part of the orbital is attracted to this part of the orbital. And what happens as a result is the overlap formed is something like this. And this is the pi bond, this is the pi bond that's formed between the lateral overlapping because of the lateral overlapping. Sometimes they ask shape of the pi bond, and that is why I just gave a diagrammatic representation. Now lastly, what I said about the strength of the bonds. Okay, now it's common knowledge that this like C double bond is stronger, right? The strength is of C double bond C is what? Okay, the strength of the C double bond C is stronger than the strength of C, right? So when I said that the pi bonds are weaker than the sigma bonds, it might sound ridiculous because why the C double bond C is stronger? It requires more energy to break. Well, if you see, I don't recall the values exactly. So these are not the exact values, okay? So for this, let's say this is 200 kJ mole minus 1. The reason why I'm saying that this, okay, no, wait, the bond energy for this is not 2x. It is something like, I think 340. If this is 200, this would be like 340 kilojoules mole minus 1, right? The reason why I'm saying sigma bonds are stronger than pi bonds is because this bond energy is formed solely due to a sigma bond, right? What is this energy formed? This is 340, right? And 200 of this 340 is coming from the sigma bond that's already present. So what is coming from the pi bond? So that would be 340 minus 200, and that would be 140. So the strength of the sigma bond is 200. It's providing 200 kilojoules of bond energy, whereas the strength of the pi bond that's present is only 140. And that's why I say that, or that's why it is the fact that pi bonds are relatively weaker than sigma bonds. Now these are not the exact values. I'm repeating again, these are not the exact values. These are just examples. But yeah, what I'm basically trying to say is that in a double bond, it's not like if the single bond is a certain value, the double bond is not twice that certain value or more than twice that certain value. It's always less than twice that certain value, because pi bonds are weaker than sigma. And the same is the case when you go to triple bonds. These form when alkynes are formed, not a part of your syllabus, but whatever. You'll see that this bond is not 3x. It's always less than 3x, because again, sigma bonds are stronger than pi bonds. That is pretty much it for the first part of the video. If you do have any doubts, please leave them in the comment section below. I hope you understood.